In the other tutorial, we were taking a look at how to assign angles and how things bonded together. I'm just going to do a quick review of that here and then hit on some of the other terms with VSEPR theory. When we bonded together water, we saw that we had two lines here between the hydrogen and the oxygen. Those are what we call shared pairs, and then around the oxygen we have unshared pairs. So we talked about how to figure out what the name of that shape was and what the angle of that was based on the number of shared and unshared pairs. What I wanted to point out here is that this all fits into our electron pair repulsion theory. Basically, the electrons don't like one another, and there's a hierarchy to it all. Here's some shapes and everything, but this is what I wanted to highlight. If you have questions on the other, take a look at the other tutorial. There's a hierarchy to how these electrons repel one another. Okay, so I'm looking right here at letter A. When we're looking at repulsion power, okay, the power that they don't like each other, in the case of water we had, oh, this is frozen up on me. In the case of water we had two unshared pairs of electrons and two shared pairs. Well, these unshared pairs of electrons really, really repel one another. That forces that these hydrogens are going to push or squeeze together a little bit more, and they'll stand that a little bit more because those are shared to shared pairs. So the hydrogens and electrons around the hydrogen will repel one another, but that's way weaker of a force than these two unshared pairs. So there is a hierarchy to that, and that's what causes those changes to the shapes. Um, so really keep in mind the number of shared and unshared and how we work on that. Now another term that comes up is this concept of a hybrid orbital. Hybrid orbitals are essentially demonstrated when carbon, that's the most common one. Carbon normally looks like this. Hybrid means it will shift that s into the p orbital to accommodate other electrons or accommodate other elements. Now also if we take a look at boron, well boron can form a molecular compound with several things. Boron has an electron configuration like this. Well, it won't satisfy the octet rule fully, so it's not a very stable molecule, but it will hybridize as well and become something like this. So it can accommodate two other atoms rather than just one fitting into this area. So those are some examples of hybridization. Now, we also talked about catenations, and I did that in the other tutorial where they will form chains with one another. Okay, so it's nice and easy to do that, and here's an example of a catenation where you see carbon will bond to another carbon, and it'll attach in the hydrogens. That is a catenation, and we can count those. Now we also talked about sigma and pi bonds. Here's what it looks like if we have a triple bond between carbons and then some hydrogens off of there. We can see they call it a p overlap, but just call it a pi bond. And we'll see a double bond and then another double bond. Okay, so those are going to be your pi bonds. Now if we get into multiple bond shapes, okay, this is isomers. It can look different ways. We can see a hydrogen. Um, what this is saying is I can form a single bond to here. Okay, so that's a 1, 2, and this double bond, just remember, is counted as 3. It's 3 shared and 0 unshared. Okay, but if we take a look at, now that's between the carbon, the hydrogen, and the other hydrogen. But if I take a look at the hydrogen to carbon to oxygen, it's going to be slightly greater than because it pulls in a little bit more, a little bit less repelling. And we're going to be seeing some different shapes from that. Okay, so that's CH2O. There's different ways to stabilize and so on. Okay, we talked about triple bonds, and we also see some really strange names like ketenes and so on when we have multiple double bonds. Okay, so just kind of seeing some of these things in action here. We're not going to worry about it too much. Now, conjugated system, you can see one in letter A here. Conjugated system, if we talk about just regular butene, okay, but means 4, and we'll get to that in a second. Normally, we would see an arrangement like this. At the end of each of those bonds would be a hydrogen. But you'll notice that there's another place that we would see a double bond. So when we get a conjugated system, that means we have a double bond not in just one place, but in another. What does that mean? What does that result in? Well, it means that this carbon can't have a hydrogen, and it means that this carbon can't have a hydrogen. It loses that capacity, and so we do need to keep track of those things, what we would find and where we would find it. So to name a conjugated system, these numbers are just going to tell me where that double bond is. I could have a 1,2 butadiene, so I'd have double bond here, a double bond here, and I'd see another single bond. What results is, well, the second carbon is full, this carbon needs one, and this carbon would need three. Okay, so we just write it a little bit different way. We'd see CH2 double bond, C double bond, CH single bond, CH3. Okay, so it's just different ways of doing it. Now I use this term or this concept of butadiene. Okay, what's that all about? Well, if you noticed with this, we're dealing with just carbons and hydrogens. Okay, I know I've got recall on here. This is something that we have not covered before, so it's new for us. An alkane means that we have a 2x plus 2 arrangement. X is my number of carbons. I use this to figure out how many hydrogens I would have. So if it's an alkane, I have twice as many plus 2 more hydrogens. So if I had, say for example, 3 carbons, okay, so it's C3 something. I want to know how many hydrogens. Well, 3 times 2 is 6, plus 2 more is 8, okay? So that's basically how that goes. Now, if I take a look and I see a double bond in here, well, actually, let me go back up a step. How would this look? This means that it's all single bonds, and if you count up the lines, I have 8 lines, okay? Now, a double bond means that I can take the same example, and now I'm going to have a double bond at that first spot for the carbon. What that means is, just like before, I'm going to lose a couple of hydrogens. So my formula for this is going to be 2x. Okay, those are my alkenes. Alkyne would be a 2x minus 2. Why is it minus 2? Well, I end up with a triple bond. Okay, this is going to get 1 hydrogen. The second, or the middle carbon is not going to get any, and then I have 3 at the end. So 2x minus 2, I have 3 carbons. 3 times 2 is 6, minus 2 is 4. Okay, so those are alkanes, alkenes, and alkynes. Mikey eats peanut butter, and then you get to pentane and so on. Meth, eth, prop, bute, and then it goes into pent and hex and hept and all that. So methane, ethane, propane. You've heard of that. Butane. Okay? If it's an alkene, methene, ethene, propene, and so on. Okay, so if I take a look at this example right here, I see a double bond. I'm thinking enes. I see 2 of them. 2 is eth. Okay, so we would call that ethene. I see an ethene. We would see two hydrogens there. Okay. Now, if I look at this one, well, I don't see the double bond at the beginning. I see the double bond at the end. So I would have to call this 1, 2, 3 carbons. Okay, so that would mean prop. And I see a double bond at the end. Okay, so it's not in the first spot, it's in the second spot. So C3, but it's in the 2 spot. And let's see if it follows the pattern. I have 3. I see a double bond. It should be an ene. So I have 3, 4, 5, and 6. Yep, it's a 2x configuration. So it's C3H6, but I would call it 2 prop because it's an ene propene. Okay, so that's how that goes. Now I could also just sketch this out. Okay, I could sketch it out in a variety of ways. I can sketch it out in terms of just basic shapes. Now this looks kind of weird if you think of the point of each of those as a carbon. I have 1, 2, 3, 4, 5, 6. I see single bonds between all of these. Now we'd assume that there's going to be hydrogens all over the place, but they're just going to be kind of all over and scattered throughout. Makes it kind of messy. I see 6 carbons. Okay? Notice that they are linked together though. Okay? It's not a long chain like I see in these above problems. I see that they're linked together. That means I'm going to lose 2 two hydrogens. So there were 6, so that's hex. It's all single bonds, so we would call it hexane. There would normally be 2x plus 2, so that would be 6 times 2 is 12, plus 2 more is 14. But since they're linked up, I would end up with not 14, but 12. Okay? We would call this cyclo, because it's all in a chain, or in a ring, cyclohexane. So I can do 2 things there. Okay? I can put in a triple bond there. What if I do just a butte arrangement? Okay? I can do a triple bond. Okay? Triple is going to be an ine. Normally it's 2x minus 2, but I'm going to have to take 2 more off of there. So there's 4 times 2 is 8, minus 2 is 6, so C4H4. Did I do that right? 2x minus 2 times 4 is 8, minus 2 is 6, so there's 2 more, C4H4. What would I name this thing? I would call it cyclobutine. I don't know why my board is slow here, but that's okay. Okay? I can do a conjugated system with this as well, and put uh, multiple double and triple bonds along the way. Okay? So here's some other ones, other examples that we would see. Okay? Conjugated system. Uh, you have different forms that could look different ways. Okay, so just be careful with those, and I think you'll be just fine.